Hello! So in this video, we're going to be going over what exactly IMFs are, and more specifically, why each IMF fits into its own category. So let's begin. So IMF actually has two separate meanings, one of them being intramolecular force and the other being intermolecular force. Now, intra means within, whereas inter means between. So basically, intramolecular forces are referring to the molecular forces within a molecule, whereas intermolecular forces are the forces between multiple molecules. So we're going to start by learning about our intramolecular forces, our forces that are within a molecule holding it together. We have three main types that we're going to talk about, which is ionic, metallic, and network. We're going to start with possibly one of the easier ones to understand, which is ionic. Yay, here we go. Okay, we're going to start with ionic, so of course we have to have everyone's favorite example of an ionic bond, NaCl. So already going in with the knowledge of what an ionic bond is, it's really easy to tell why this force is intramolecular as opposed to intermolecular. Really, all it is the positive and the negative ions attracting each other. This little bond that they have together is the intramolecular force. It's what's keeping it together, is that opposite attraction. And that's as simple as that one gets. Next, we're moving on to metallic, which is our next intramolecular force. And this is basically the reason why pieces of metal can exist. So we know that metals are always positively charged, so therefore they need something negatively charged running throughout the molecule in order to keep it together. And metallic bonding has its own special IMF called delocalized electrons, which are basically electrons that run throughout the whole entire molecule, distributing an even negative charge throughout the whole entire piece of metal. And basically, that's what we need in order to make sure that these positively charged metal ions aren't repelled from each one another. So that's why this is an intramolecular force. It's because it's happening within the whole molecule of metal, like aluminum or really any metal. Aluminum, copper, all those fun things.
Okay, so now we're going to take a look at our final intramolecular force, which is network bonding. You see network bonding a lot in your precious stones such as diamond and quartz. We're going to take a look at diamond, actually. And we see in this diagram that it's actually just a bunch of carbons that are covalently bonded together. And what makes this covalent bond intramolecular is the fact that it's not multiple molecules being bonded together, but it's rather one very large macromolecule. And this repeating network of covalent bonds between all the carbons is what gives stones like diamond and quartz really great hardness. Without further ado, we're going to start talking about our intermolecular forces, the forces that are between molecules. And we're going to start by talking about London dispersion, and this is because you can't have polarity without London dispersion, and you can't have hydrogen bonding without polarity and London dispersion. So that's why we need to start with London, because it's involved in everything. This is going to be a very brief explanation of what London dispersion is, but basically London dispersion occurs between all molecules whether or not they're polar or not. So looking at this bottom diagram, we see two molecules, two of the same molecule, and each of them has a positively charged end and negatively charged end. And what these are called is dipoles, which gives London dispersion the other name of dipole-dipole attraction. Dipoles occur basically because electrons are constantly moving around a molecule, making inevitably a time in which there's more of a negative charge on one side than the other side. And that makes it a very temporary weak attraction since they're constantly moving. But basically, a positive dipole of one molecule will attract to a negative dipole of another molecule. And we're going to look at water a lot throughout our talk about intermolecular forces. But basically, let's identify the London dispersion force between two independent water molecules. So we see that the negatively charged oxygen is on one side of this water molecule, and there's more of a positive charge on the other side of the molecule from the positively charged hydrogens. And the negatively charged oxygen is attracting to another water molecule's positively charged hydrogen. But of course, these water molecules they're always constantly moving around, which means that they're going to disconnect and connect with other ones simultaneously very, very quickly, making it a temporary weak attraction. Okay, so polarity is, as it said right here, an unequal sharing of electrons. And we looked at water, which is what we have right here, just before with London dispersion, but it's actually a much better example for polarity. London dispersion has temporary dipoles because the electrons are always moving around, but water's different since it's polar. So water has oxygen, which is negatively charged, and it's slightly more electronegative than the positively charged hydrogen, meaning that it's always going to take all the electrons for itself. Not all of them, but a lot of them. And the hydrogen is trying to give them up just a little bit more than oxygen is. So that makes for a permanent imbalance of the electrons, making the dipoles more permanent than they are in your plain London dispersion case. Okay, let's take a look at our last intermolecular force, hydrogen bonding. This occurs when a hydrogen is bonded to an F, aka fluorine, an O for oxygen, or an N for nitrogen. So you can also call hydrogen bonding if you wish to do so. But basically, water is a great example because you have the negatively charged oxygens bonding with another water molecule's positive hydrogen, and that's all you really need to know about hydrogen bonds. So now we're going to move on to identification. For intramolecular forces, that's actually very simple. You'll know its network if it says diamond or quartz. You know it's metallic if it just says Al or Cu or any metal. And you know if it's ionic if in the name you see a metal bonded to a nonmetal. That's as simple as that gets. Really, where it gets a little bit more complicated is with intermolecular forces. Okay, let's identify some intermolecular forces. We identify intermolecular forces through the Lewis dot structures, and we're going to look at some examples that aren't necessarily water. So here we have the covalent bond of sulfur hexafluoride, and we know that every covalent bond has London dispersion, so that's a yes. Now our job is to figure out if it's polar. So we see here that the sulfur hexafluoride has 6 bonds, 1, 2, 3, 4, 5, 6, and there's no lone pairs in the central atom, making the number of this Lewis dot structure 6, 0. And we know from our VSEPR structure knowledge that 6, 0 is not polar. So since it's not polar, that also means that there can't be hydrogen bonds. So that leaves us with sulfur hexafluoride just being plain old London dispersion. Okay, so now we're going to take a look at what we have here is phosphorus trichloride. Let's take a look at this. So we know it's covalent, so it's most definitely London dispersion. Now let's figure out if it's polar or not. So we have 3 bonds here, and we have 1 lone pair in the central atom. And that means that it is in fact polar because 3, 1 is indeed polar. And we know there's no H bonds because there's no hydrogen at all involved in this whole entire molecule, let alone hydrogen being bonded to FO or N. So this is just it. It's London and polar. Okay, so finally we're going to look at our last example, which is of hydrogen trinitride, aka NH3. And so we know it's covalent, it's got to be London, and before even going in to identify whether or not this is polar, we see hydrogen bonded with an N. And recall it can be bonded with an F, O, or N, so we know there's hydrogen bonds, and if there's hydrogen bonds, then it's by definition polar, and that's all you really have to do for this one. I hope you found this video helpful in learning the ins and outs of IMFs. Thanks for watching.